Okay, and now what's the most reactive thing? And this one does become a little bit tricky. If we go to negative oxygen, what could that negative oxygen act as? A base or nucleophile. Both of those are open access. Okay. Why would it act as a base? Because actually it does act as a nucleophile. 100% it does.
Oh, yeah. Do you know that?
For me, it acted as a base.
No, it acts as a nucleophile.
How? But
Breaks the pi bond, right? We reform the pi bond in the second step, and what do we kick out? The leaving group. What's the leaving group? OET or?
Is it the?
Or? What does ET stand for?
It kicks out the one to the
Extraterrestrial.
right. Are you fucking serious? This is stupid. This is so goddamn dumb. I hate this already.
The oxygen comes in and attacks, breaks the pi bond, forms a tetrahedral intermediate. We reform the pi bond and we kick out our leaving group. What's our leaving group? O with 2 carbons or?
The one with 3.
O with?
Two. Oh wait, never mind. That's 2 carbons.
2 carbons.
Whoops.
Does it do the nucleophilic attack?
No.
It absolutely does. There's nothing wrong with that. That is perfectly valid and legit. Does it change the product? No. The base used in this particular reaction is chosen very carefully, because if the base isn't chosen correctly, you get the nucleophilic attack and the acid-base reaction. And because the nucleophilic attack results in a different structure, you get a ton of different materials. So it absolutely still acts as a nucleophile. It just so happens that the product produced in that nucleophilic attack is the exact same thing as our starting material, which then means
It doesn't happen? Or does it matter?
it's irrelevant to the question, yes. So what could it do instead? That's where, yes, we can go through and say it can attack our hydrogen and we can form our negative charge. Yes, Irvin, go ahead.
That's why it is not reacting with the first order with the other carbon.
What happens if it reacts with the other carbonyl? I left that one out of the conversation. I thought about discussing that. Should I draw it?
I mean,
Well, there's no leaving group.
it would just leave again. It would just immediately leave.
True. What does it produce when it reacts with the other carbonyl? Say it again, louder. An acetal. Officially not an acetal. What it's forming is the hemiacetal. Okay, to get the acetal, we actually can't get to the acetal under basic conditions, because to form the acetal under basic conditions, you need to run an SN2 reaction, and it's not SN2 capable. Okay, but ultimately we do form the hemiacetal, and what do we know about our hemiacetals? They're unstable and they revert back to the carbonyl. So it can still nucleophilically attack that, but again, it's resulting in effectively a dead end that doesn't do anything for our chemistry. So this particular structure, starting material, has 3 active, technically 4 active reactive sites. Okay, where's the 4th? We just talked through 3, right? Where's the 4th? Come on, Skywalker. Where's the 4th?
The other carbonyls.
Alpha hydrogen, yeah, there's an alpha hydrogen out there. Why should we select the green hydrogens as opposed to the purple?
Way more acidic.
Why is it way more acidic? The double resonance. Cool. Okay, so cool. That's the result of step 1. What do we do with step 2? Our most reactive thing is now this negative carbon. Okay, and we bring in step 2.
That attacks the carbon.
Whoops, CH2PH. Okay, what is that bromine good at doing? Leaving, which means our carbon becomes very partially positive. Our nucleophile can come in and attack. For 6 steps, I am not pacing my spacing very well. That's patronizing. I mean, it's appreciated, but it's still patronizing. Okay, so our CH2PH. What's the next thing?
The same as the first one?
Yeah, it's the same as the first.
So,
Right? Negative oxygen, so what's it going to do?
well, it's going to do all the other shit before, but then it's going to do the same thing again because there's another hydrogen.
There's still an alpha hydrogen there, so that can still go through and
Wait,
react.
well, why wouldn't it just react again in the first step? How much is added in the first?
So why did the ethoxide not pull off 2 hydrogens? What would the charge be on that carbon if it pulled off 2 hydrogens?
Oh, that's right.
It would be a -2. That's not stable. We can't do that resonance to
that's not
stabilize it.
considered, that's right.
Right? So it does end up having to get split into multiple steps. I need to face the board because the structure is obnoxiously large, and I'm trying to do better with my spacing. I'm going to turn it the other way. Here's my negative pair. Now what happens? Look, sorry. Did I not hit anybody? Okay, good. Now what happens?
I guess the CH3 from step 4 would then come in and act as an electrophile.
We've got that iodine connected to that carbon. That iodine's a great leaving group. There's a CH3. I guess we should color code that. CH3. Now what happens?
No, those reactive thing it's in the OH.
Now we bring in an OH minus.
The question is it act as a base or a nucleophile?
Ah, good. I love that. Does it act as a base or a nucleophile? Well, when we started this whole question out, what did it act as?
Yes.
Yeah, okay. Okay, in the first case, when we started it all off, the bases we use, ethoxide, when they acted as nucleophiles, didn't do anything productive. It didn't change the structure. Would it change the structure now?
Yeah.
Yeah, it would. That ethoxide can come in, break the pi bond. We're going to do the lazy man or lazy person. Let's go. Not gender this. Okay. Our lazy person synthesis, we're going to eject that as our leaving group. And what we would end up with would be okay, which is actually technically incorrect.
Because
Okay, so Charlotte gave me an O. What was the O about?
I thought that oxygen left on the end. Where'd you draw it right there? It's from the OH. Oh.
Okay, so we're gonna, because you at least acknowledged the O and said something weird is going on here.
Yeah.
Did you figure out what the weird thing was when I drew this product? Still haven't figured it out? Okay, if we process it up, okay, the OH comes in, attacks our carbonyl, so we'd have our tetrahedral intermediate. Okay, we break the pi bond up to our oxygen. The pi bond reforms, we reform the carbonyl, and we kick out the OET. So what we'd be left with is a carbonyl and OH. Carbonyl and OH.
Yeah.
So why would you question that? I mean, that's all right there. Why does this look weird to you?
you just positioned it weird.
I positioned it weird. I did a weird, goofy bond rotation, right? Am I allowed to do that bond rotation?
Yeah, it's gonna do it.
Well, it's the same thing.
It's a sigma bond, yeah. It's fully allowed to do that sigma bond rotation. So that's absolutely fair game. I'm allowed to do that. Okay. Why I did it becomes another matter that we'll deal with in a second. Hold your horses. Okay. Because first, if we enter this for 5, they should be telling us we're wrong. Okay. But I'm going to actually pull up the solution just to make sure.
I put it as well.
You did draw this in and said it was wrong? Good. Why is it wrong?
Well, it's gonna do the reaction.
It's a carboxylic
Acid?
acid. What conditions were we under in step 5?
Base.
Basic conditions, what's going to happen?
It's going to deprotonate.
It's going to deprotonate.
So that there would be a negative oxygen there.
That should show as a negative oxygen. That should set you up for the correct answer, 5.
Why'd you say that I had to position it like you had brain damage?
Because I could look ahead. It's a chess move, bud. You can't see the chess move yet. Okay, what happens in step 6?
What about the water?
The water is ultimately just a solvent. This is where it could be a little bit questionable. They're trying to say the water protonates that, and that's bad mojo. Water is acting as your solvent, probably help facilitate the proton transfers in the varying intermediate states within your mechanism. You're not being asked for the mechanism, so who cares? I mean, I don't. So what happens in the next step? You gain that hydrogen back. Because it is officially another step, I'll go ahead and draw it out.
This is another time where you add the heat just to fuck with us.
Nope.
Oh, no, it actually does something.
Yep. Okay, so we put the hydrogen on. There's step 6. We enter it into SpartWork, and SpartWork says, you're wrong. Damn. Okay. There was a reason we did this reorientation of the molecule. Okay, you ready for that reason? It's fun. Guess what that oxygen on the carbonyl that's been sitting out there not really doing much has? Lone pair electrons. What could it do with those lone pair electrons? It could share them. Yeah, it could act as a base. It could share them with that hydrogen that is conveniently oriented in a way that's very, very close to it, forming what would effectively be a 1, 2, 3, 4, 5, 6-membered ring. 6-membered rings are allowed to form. So that hydrogen could oscillate back and forth between those 2 oxygens. That's fair game. You'd be like, well, why does that matter? Not quite matters. But it picks that up. Where do the electrons in that oxygen-hydrogen bond then go? They could go to the oxygen, but it's next to a carbonyl. We like resonance. Let's take those electrons from that bond and shift it to another bond to make a double bond. Okay? When we did that, we would exceed the octet on our green carbon, right? And what would we typically do?
Say that's bad.
We would break the electrons, or we would shift the electrons in that pi bond onto the oxygen, and we've got resonance. Ta-da! Except what else could we do to fix that exceeded octet on that carbon? We've got that sigma bond to the carbon right there. We could do that. Is that legal?
That's not what I was going to say, but yeah. I was thinking that 6-membered rings are notoriously, stable.
They are notoriously stable, which helps to explain why that hydrogen can float up to the top. Okay, what happens to the rest of it? Okay, we'll try and draw it somewhat kind of close in all these proximities. There's our double bond. We didn't touch the other double bond. And we'd have a negative carbon. Can we have a negative carbon?
With resonance.
With what?
Resonance.
Is there resonance here?
No.
It rhymes with fess.
Yes.
What functional group have we created?
Enolate.
Yeah, that nice little purple system right in there looks an awful lot like an enolate. Yeah, the deep sigh. It's a good one. Gotta love it. Okay. Officially, we'll end up losing that hydrogen as well, but what we'll end up with is a final product, because that enolate is going to, number one, stabilize that structure as a leaving group. Sorry. Am I still doing well? Can you see that product up in that corner?
Yeah.
Okay, fine. And we would eject CO2 as a leaving group. So CO2 isn't a leaving group. CO2 is just floats off the structure. So we create CO2 as a phenomenal thing that just kind of falls off the structure, uber stable. And the enolate, since it's resonance stabilized, is a great leaving group. Okay? That then goes through its tautomerization to revert back to the carbonyl, and what we have now done is ended at our final product.
That wasn't nice. That was not a nice
Okay? And that reaction happening at the end is not a nice reaction. A lot of students struggle with that one, and I don't blame them at all. I would argue it's a really important reaction, because what did we produce?
CO2?
CO2. Where might we see the formation of CO2 become relevant for us?
Combustion.
To push it a step further than just straight up combustion. I mean, it's technically combustion.
Breathing?
Your whole existence is revolving around the production of CO2.
I was going to say soda, but I think that's pretty important.
Okay. What we're looking at is what's known as a decarboxylation. Decarboxyl, so the carboxyl is your CO2, and D because you're removing it. Okay, you have to have the proper alignment of those groups to facilitate the decarboxylation reaction. Okay, so ultimately what this big sequence of steps is doing acid-base substitution, acid-base substitution. All the first 4 steps are all really straightforward, effectively OChem 1 chemical reactions, just with a goofy new big looking structure. Okay. Reaction 5 is this unit. Okay. Legit not transesterification. This is does it have a name? Saponification. Because you're taking an ester and turning it into a soap molecule. That's why we call it a saponification. Okay. That final, or not that final structure, but then this goofy thing is what sets us up for the proper alignment for the decarboxylation, which happens in question 6, which is, again, this particular unit. Okay? The decarboxylation as a reaction is pretty neat, or this whole cycle is pretty neat as a reaction, because if we go through and look at this, we're able to make carbon-carbon bonds, so we can make a larger, more extensive structure. Okay, this one we actually made a significantly extensive structure because we ran 2 substitution reactions as opposed to just 1. But if we consider it as just 1, what we are adding to our structure is 3 carbons. 1, 2, 3. The 3 carbons sitting on that carbonyl are all added to our structure. So if we think about synthesis and how we build things, we want to add more carbons onto a structure, but we want to add in very kind of structured mechanisms. Okay? Systems that allow us to be very repetitive and precise within our protocols. Okay? This allows us to add 6 carbons, and not only 6 carbons, but relatively easily. If you go through and look at the conditions behind these reactions, we're talking about alkyl halides. Those are straightforward. Look at the bases used. Sodium methoxide, sodium hydroxide, all those are strong bases, but those are incredibly common strong bases. Those aren't stupidly strong to generate carbon nucleophiles. Those are actually relatively weak in the grand scheme of the bases that we've used this semester. Right? That's pretty amazing. We can get away with using very simple bases and get larger carbon structures, okay, and repeatable larger carbon structures. That's kind of neat. Okay? So synthetically, it's super powerful. You'll see it referenced a lot within the different chemical reactions. You'll see them pop up. Decarboxylation is the name behind it. And if we, I'm trying to think, there's another name that I think goes with it. The acetoacetic acid or the malonic ester synthesis, I think, follow the same patterns. They end with a decarboxylation. And so what they're talking about is how many carbon structure or carbons you're adding to your overall structure. Okay? And the name, the acetoacetic or malonic ester, has to do with the starting material you're using, this thing. Okay? And of course, not a usable name, it's a common name associated with them. So those are named reactions, but they're named after the chemical that you're using, and unfortunately a common name, so it's obnoxious. Okay? What's up, Ivan?
I guess we can do D next.
Okay. Did they really? Sorry, I'm really curious now. We're going to delete everything. Sorry. Hope you're good at that. What was it? Step 5? You can show me the answers. Oh, you twits. Oh, did they not? They don't even tell you. Man, how heartless. I wanted to see that they put that negative charge in there. Oh, well. Okay, you said 5, the same chapter?
Do you, on the opening thing?
Sounded like lunch got in the way, but I think open exam, did you say D?
Yeah.
Okay. Oh, I love this one. This is not a 5-minute question. But we can start it. Complete mechanism for the reaction of the generic Grignard reagent shown with the cyclic ester. There are 2 grading paths on this one. Okay? If you run me the standard Grignard ester mechanism, fine, great, 7 points. If you actually recognize the hidden chemistry behind this, that actually takes us to the official product, which is shown in 2, okay, you get more bonus points. Okay, so it's Grignard. So when we look at our starting materials, what's our activity? What's the most reactive thing we see? Try again.
The carbon
Try
enters
again.
Magnesium bromide.
The magnesium bromide structure, that carbon is going to be negatively charged. With that carbon being negatively charged, we now have a great nucleophile or base, which may become relevant later. Don't think it does. And as a nucleophile, if we're thinking our Grignard reaction, what's going to happen? Should attack the carbonyl. Boop. Breaks open the carbonyl bond. Why do we not protonate the carbonyl first?
Well, because it would immediately be deprotonated by the Grignard.
Well, there's no reactivity.
I believe you all answered it, but there were 3 people talking all at the same time. Okay. I think one person said there's no acidic hydrogen. Okay, and I think somebody else was referencing that if there was an acidic hydrogen, it would quench the Grignard. So it's talking at 2 of those points. Okay, those were the 2 answers I heard. Did I cover what everybody said? Yes?
Said there's no reactivity,
What do you mean there's no reactivity?
but as you said, why it doesn't protonate first, like the carbonate.
Yeah?
That option has a partial negative charge. There is some reactivity.
Yeah. If we were under acidic conditions, absolutely 100%, you should be drawing that carbonyl getting protonated. Absolutely. Okay. It can't run under acidic conditions because it's the Grignard. So we form our tetrahedral intermediate, so now what happens?
The
Second step?
What did you say? I don't know what second step means.
The second step to protonate the oxygen.
Protonate the oxygen. Okay, so you're saying second step, which interestingly enough is not actually listed here. Okay, so that's wrong. Okay, and 2, resonance, I must say is also wrong because there's not resonance.
all the electrons move back down.
Okay, I accept that. The electrons can move back down
And break the bond to that oxygen.
and kick out the leaving group of our oxygen. Yes. Oops, I'm in black. I can do that.
That number 2 is really intriguing.
It is. I believe this is actually a named reaction. I stumbled across it and was like, holy crap, what the hell is going on? And I was like, oh, actually, that's kind of neat. We should turn it into an exam question.
Oh, yeah.
Okay. And because we've now touched the other oxygen, we'll go ahead and include its lone pairs too.
Just that. The fuck?
All right. So if you're struggling with question 2, or part 2, let's not stress about that necessarily yet. Right? Because we got 7 points on the table, and if we understand our Grignard reactions and our esters, we should be good. Okay? Is this now the standard product and we're now done? No? What's up, Josie? Hit me with it. You got it.
They're not connected.
True, they're not connected, which would be 2, but if we're pushing to the standard answer, something else is going on.
Can the Grignard attack the carbonyl now?
The Grignard would typically attack our carbonyl again. When we talk about Grignard reagents with esters, they react twice because the product that is formed is a ketone. And if we think back to the ladder where we talked through the reactivity of our acid derivatives in comparison to our aldehydes and ketones, our ketones are more active than our esters as far as electrophiles. And if they're more active, the Grignard would likely attack the ketone a second time. Okay, so we go through and run our Grignard reaction again. RR with the lone pair electrons, come in and attack, break open the pi bond. We'd have our new Grignard piece, have our old Grignard piece, and then we'd have our oxygen with its lone pairs and that negative charge. Yeah? Okay. That would be following kind of the standard Grignard path. Okay. To Abby's complaint, not complaint, comment. Let's go with comment. Comment's better. Didn't really complain. Okay. When we consider our Grignards, we almost always follow them up with H+. So we could go through and say, well, now we'll go ahead and protonate, and all would be fine and hunky and dory, and we would get our full 7 points for our path 1, the standard product.
So if with this specific question, if we did not add that final step,
So when you say final step, it's problematic because it's not one, it's several. Okay, but to get to product 2, okay, it's not one extra step. But if you opted to not do that, you just got 7 points.
no, so I'm talking about, say, if you didn't add the hydrogen to the end of the Grignard standard.
I would still give you 7 points for what's shown on this
Okay.
because technically there isn't a hydrogen shown in that. So you got an easy complaint to be like, but Mike, it's not there. And I'd be like, ah, crap, you're right.
Okay, gotcha.
Okay. So everything that's shown here would get you 7 points. 2, 3, 4, 5, 6. And if you go through and look at it, you've got several structures, several arrows. So if we consider all of that together, you look at the amount of arrows and the amount of structures, you're hovering right around 7 different things. That's why it's 7 points. Okay, a point for each aspect behind that. Okay, but we want more, right? We want to figure out what the hell's going on in step 2. Okay, so to figure out what's going on in step 2, we're going to revert backwards a little bit. And delete that. We identified that functional group as a ketone. That's actually kind of cool. It's kind of neat. I like that. But what we're going to do is, again, erase all that. And what we're going to ask ourselves when we look at this structure is, yes, there's a ketone there. What else is there? What was that? What was that? There's an enolate. And what could that enolate do? That could tautomerize. It's going to be a couple mechanistic steps. And because we're out of time officially, I'm not going to draw all the mechanistic steps. Okay. So it tautomerizes. We've got our enolate. So that's different. But does that look like answer 2?
No.
No. What has to happen to get to answer 2?
The 2 ketones just form together. Like it does some kind of reaction where they just melt.
Well,
So let's lean on that because I really don't like your wording there. But I think I understand what you're trying to say. Is that somehow or another, those 2 pieces have to somehow react. Well, what 2 pieces? You said the 2 ketones. I would argue the 2 ketones do not react with each other. Because if we go through and look at structure 2, I still have a ketone. So the ketone is not reacting in one case.
Ketone have to react with the R on the.
That one ketone is interacting somehow with that carbon. What chemistries do I have at those positions that would potentially allow for that reaction to continue? And for those of you looking forward to that exciting answer, that's next week.
Oh, you son of a